Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hello everyone, and welcome here. Today we have Xusheng from North State Carolina, who's going to talk about work he's done in PECs and work about helping users understanding what the dynamic symbolic execution engine tells them. It's very confusing, and he's been done a lot of work trying to help them in two areas. So we're just going to let Xusheng work about that and maybe introduce himself a little bit deeper.
Okay. So, hello everyone. My name is Xusheng Xiao. I'm a second-year PhD student in North Carolina State University. My advisor is Dr. Tao Xie. So this is the collaboration work with the PECs group. Yeah. So to ensure the software reliability and quality, software testing is by far the most widely used testing techniques. So one of the testing techniques that is used extensively is structural testing. Structural testing is test the internal structure or working of the programs. It's also called white box testing. So structural testing usually executes the program under test using different test inputs, and it measures the achieved structural coverage. For example, the most commonly used is the statement block coverage, which measures how many % of the statement block is covered by the test cases. And the other one is the branch coverage, measuring how many % of the branch is covered. So an important goal of structural testing is to achieve at least high structural coverage, because high structural coverage can help you identify the insufficiency of the test cases. For example, it can tell you that which part of the program is still not executed by your test. So you may considering providing more test inputs to test that part of the program. So to produce the test inputs that can achieve high structural coverage, developers and testers can manually produce such test inputs. But as we know, it is labor intensive and it's tedious. So usually we employ automated test generation tool to automatically generate test inputs. So to automatically generate test inputs, we can employ random approach. So the random approach is I randomly select the text inputs across the input space. This approach is the test generation of random approach is cheap and fast because the random algorithm usually perform very well. However, the generated test input usually achieve low structural coverage, especially when the program have complex control structures or only a subset of the test input among a large input space will achieve high coverage. Then the random approach will have low probability to produce such inputs. So the other state-of-art test generation approach is dynamic symbolic execution. So dynamic symbolic execution is not random. It's based on constraint solving. So basically, it executes the program symbolically, collecting the constraints from the conditional statement, use the constraint solver to produce text inputs, and then explore the further parts of the program. So although dynamic symbolic execution, I missed one point, is like the state-of-art dynamic symbolic execution tool is PECs. Yeah. And so although the dynamic symbolic execution can simply achieve high structural coverage for simple programs, it usually faces different kinds of challenges in dealing with the complex program in practice. So here I give an example. I apply PECs on an open source project XUnit, which is used by many developers in real project in practice. So when I apply that, PECs face different kinds of problems. The first problem it faces is called the external method call problem, where the tools cannot deal with the external the method call to the external library. By external library, I mean the library to the native system calls, like file system or network socket, and all the pre-compiled third-party library, which normally your tool will not automatically deal with them. And the second problem is the object creation problems. So in object-oriented program, to cover certain branches, it may require you to create some object. To create the objects, you need to produce a sequence of method call to first create object, and then you need some state modifying method call to modify the state of the object so that you can cover certain branches. Later, I will give more example on these two problems. Okay, so to study what problems preventing automated text generation tool from achieving high structural coverage, we perform a preliminary study on 4 open source projects. So we apply PEX to explore the public method of these 4 projects, and we collect the achieve coverage and study the problems. So as you can see, the total block coverage achieved is about 50%. With the lowest, it's just only 15%. So which means that we actually face many problems when we apply on complex program in practice. So the top major problem is the object creation problem, which like PEX cannot generate desirable objects for some certain branches. The second top problem is the external method call problem. It's like the problem happens when the return value of some external method call is used by the subsequent branches. Then PEX cannot generate the test input to force the external method call to return the desired value, so the branches cannot be covered. Or the external method call may keep throwing exception when PEX generated invalid input. So it abort the test execution and PEX cannot explore the remaining part of the program. The third type is the boundary problem. It usually happens when PEX exceeds the boundary of the resources before it can reach a certain amount of coverages. Typical example is like PEX may keep increasing the iteration number of a loop, and it will not handle the remaining part of the programs. So the fourth problem is the limitation of the use constraint solvers. So like as you can see in the third subject math.net, here we have this kind of, because this library involves many floating point computation, which is the limitation of the used constraint solver. But yeah, although like the constraint solver can give some approximate integer, but still some branches he cannot cover. Yeah. So in my current work, I focus on the first 2 major problems because they account for the most problem. Yeah. So next, I will give you an example like how external method call problem will prevent automated generation tool from achieving high coverage. So we can see that from the code problem 1, we said there is a external method call file that exists. So this external method call receives the argument of the variable configure file name. Actually, this configure file name is used the data defined by the program input. So we know that file.exist actually has data dependency on the program input. To cover the branches at line 1, at line 1 the conditional statement, the test input should cause the file.exist to return the true value in one test case and false value in the other cases. But unfortunately, because the tool cannot analyze this external method call, so usually it cannot achieve the full coverage of these branches. The second example is a little bit similar. It's like the pass.get4pass. This method call also has data dependency on the program input. But this time, this method actually checks the argument, the validity of the argument. So if you generate an invalid input, this method keeps throwing exceptions. And if across all the test executions, PEX cannot figure out how to generate a meaningful input for these methods, PEX cannot explore the following part of the code. And the third example is some kind of the external method. They have data dependency on the program input. They also have return value, but their return value is just used to print out some strings. For example, like string.format. Such kind of external method actually does not cause any problem to the text generation tool. So we need to identify these 3 cases and filter out the irrelevant candidates. And here is an example for object creation problem. So we have a class called the fixed size stack. It uses the classic implementation of a stack. So the stack is like you cannot just assign a list of size to the stack. You need to call the push to increase the size of the stack. So we have parameter. We have a parameter unit test like called test push, which is just like simply test the push method of the fixed size stack. So to cover the branches at line 5, we need the 2 branches of line 5. We need a special method called sequence to generate a stack whose size is 10. So the sequence will look like this. So you first create a stack, and then you call push 10 times. When you get a stack object, you invoke the constructor of the fixed size stack and you pass in the stack. However, this method sequence will be very difficult for many tools to generate, because the tool cannot figure out like if I call push, I increase the size. I may call push first and then I call pop, then my stack go back to the empty state. So I mean the search state for this is very huge and very difficult for a tool to figure it out. One observation we can see is like, actually you can see that if this branches is not covered, we can find that this branch actually has data dependency on one of the field of these objects, which is the stack.items. Yeah, later I will give more detail on this. So to address this problem, we propose a new approach, which is called cooperative developer testing. So when the tool is not perfect enough to deal with all the problems, human can kick in and to help the tool. So in our example, like we can first apply the tool to generate a test. After the tool generated the test, the tool can report it the achieved coverage and report it the encounter problem during the test generation. So when the developer look at these problems, he can provide some single code snippet or some help to the tool, and then and then he can apply the tool to see the coverage increase. For example, when you see an external method call problem reported, you may think of like, maybe I can ask PEX to instrument and explore this external library, but it's not guaranteed. Or like if I think that, okay, I'm doing unit testing, I can mock this object. So I provide some mock object for only the external method code that is identified as the problems. And for object creation problem, we can actually provide factory methods. So we can just write a code snippet to guide the tools how to generate the method sequence to increase the size of the stack in our example. Yeah. So there are some existing solutions for problem identifications. So the very easy way is like I can just report it every external method call encountered during my test generation and executions. Or I can report it all the non-primitive object type of the program input and their fields. However, the limitation of this approach is that the number could be high. People don't want to look at all the problems because I later will show an example to see that. And also, some of the identified problems, they actually are not relevant. Even you like provide guidance to them, you may not help the tool achieve coverage. So we need a way to precisely identify such problems. Let's go back to the previous example. So we can see that here, like PEX report 44 external method call problem. It reports 18 object creation problems. But however, when we manually investigate all these problems, we found that none of these external method call actually will cause problem to the tools. Like you can just skip them, and actually only 5 of the object type would require human help. So we propose an approach called Covana. Covana is aimed to precisely identify the problems faced by the tool when the tool are achieving the structural coverage. So based on our preliminary study, we have insights that actually we found that some partially covered statements, they have data dependency on the program candidates. So our approach contains 3 main steps. The first step is like we will identify the problem candidate. For example, for external method call, we first need to identify which external method would be the candidate for our analysis. For object creation for object creation problem, we need to identify the non-primitive object type for our analysis. When we identify the candidate, we will perform forward symbolic execution on this problem candidate. So we basically assign symbolic value to the return value of the external method call, or we just simply assign symbolic value to the non-primitive object type of the program input. So, and then we perform the forward symbolic execution. We collect the runtime information and achieve coverage. which will be used in our later stage data dependency analysis. Then we identify, okay, which candidate actually is a real problem, which are not. Then we prune the irrelevant candidate. So this is the overview of our approach. So the input of our approach is the program or the parameter unit test, and the test input is generated via tools. And the output of our approach is the identify problem. So when we have this, we just tell you that what's the problem of the tool. So we first perform forward symbolic execution using the text inputs. The reason why we do this is that we want to collect the runtime events when you executed the generated text input, so we can identify the problem candidates. So I will give an example to show them. So for external method call candidate, we don't consider all the external method call as the candidate, because if the external method call does not have data dependency on the program input, it varies in a constant string. So it's very likely that this method call are just print constant string or just put a thread to sleep. We don't need to analyze such external method call, which usually will not cause problem from achieving higher coverage. For example, here we have an external method call file.exist. When we look at it, we can see that this we use the variable assembly file, and actually this assembly file is used one of the value from the program input. So we know that this external method call has data dependency on the program input. So we identify it as a candidate. Similarly, for this method, we can also use it directly use the program input as the argument. So we know that this is one of the candidates. For identify the candidate from the object creation problem, we simply identify the non-primitive object type of the program input. So yeah, we don't, because for primitive type int, boolean, double, you don't have such kind of problems. So for example, for this PUT, we can see that the program input is the fixed size stack on the object. So here we identify the program input as a candidate, and all its field will be collected, also identified as the candidate. So the next step is we will perform a symbolic execution on these program candidates. First, we turn the elements of the program candidate to symbolic. For an external method call which is identified as candidate, we turn its return value as a symbolic value. For the object creation issue, for object creation problem, we assign symbolic value to the program input and all its fields. Then we can leverage the symbolic execution engine to perform forward symbolic executions. For example, in our current implementation, we use the symbolic execution engine of PEX. And then we collect the runtime information. The runtime information including the symbolic expressions in branches and the uncalled exceptions, which will be later used for our problem analysis. Okay, so I will walk you through using some examples. For example, we can see that this is an external method called identified as candidate. We turn its return value as the symbolic. So we can collect a constraints from the branches at line 1. Then by extracting the elements from the constraints, we can know that the branch statement at line 1 has data dependency on the external method called file.exist. Using this data dependence analysis, we identify the real program the candidate should have data dependency on the program input, and its return value is also used by some not covered branches. For example, here we already know that it has data dependency on the program input. And then we found that the fourth branch at line 1 is not covered, which means that line 1 is a partially covered statement. And then we report file.exist as a real program. Yeah, so the second analysis for identify external method call is to analyze the exceptions. So we collect the uncalled exception during the test execution, and then we extract the external method call from the stack trace from the exception trace. And then we check whether the remaining part of the call side is not covered. For example, this method slow exception for all the executions. So we also check that the code after line 6 is not covered. So we know that the remaining part of the program is not covered. then we further confirm that, okay, pass dot get 4 pass is a real problem. So similarly to identify object creation problem, we also use the similar technique to analyze the data dependency. So if a non-coupled branches has data dependency on the on non-primitive program input, like if you directly depends on the program input, for example, you may have like object stack cannot be null, then you can just report a stack because you need to first provide a stack. But if you depends on the field, can we just report object type of the field directly? Let me give you an example to show this. So for example, we can see that here, this statement, this method returns the size of the field stacked items. So we know this statement has data dependency on this field. And then we further found that, okay, the true branches is not covered. So if we directly report the object type of this field, we will report a list with objects. However, this is the false warning. Because even you provide a method called sequence to control list, the fixed size stack cannot use it because this list cannot be assigned to the field stack.items directory. You cannot find any public constructor or public setter to assign this external object to the field. Therefore, to address this problem, we provide a field declaration hierarchy analysis. So first, we control a field hierarchy from the field up to the program input. In this case, it will look like this. To construct this field declaration hierarchy, we can use reflection to do that. So we start from the program input and then we looking for the field level by levels until we found out the field we want. Then to do that, we need to analyze the field level by level. For example, if we depending on the program input, as I expressed earlier, then we just report it. Then later we check whether this field is assignable for its declaring classes or not. If the field cannot be assigned, for assignable, I mean if this field can be assigned external object using the public constructor or the public set method of its declaring classes. So if it cannot be assigned, then we're just reporting its declaring classes. If the field can be assigned by its declaring classes, we can keep track until we report the field itself. So I give you an example to illustrate the analysis. So we have this field hierarchy. We first check whether the fixed size stack can be assigned using the public constructor or setter of the fixed size stack. And we found that, okay, from the constructor, we can see that we can pass in a stack, and this stack can be assigned to the field. So we keep going, checking the next step. So we check that, okay, we found that stack.items is not assignable. Then we report the stack as the object type for the object creation problem. And when this is correct, when we provide object create factory for it, the PACS actually can pick it up and generate test cases to cover these branches. So we implement our approach. Part of our approach is implemented as an extension to PACS. So this is to identify the problem candidates, assign 10 elements of problem candidate symbolic, and we also need to collect the runtime information from PACS. And the data dependency analyzer and the GUI opponent is implemented as a C# phone application. It's just to analyze the collected information and showing the analysis result. So our tool is released public available on the PACS extension website. To evaluate our approach, we choose two subjects. The first subject is XUnit. It's a unit testing framework for .NET. It's a popular testing framework used by many real projects in practice. The other one is the Quick Graph. It's a C# graph library. It's also used by many projects because our approach is tend to analyze the problem for the complex problem in practice, and it's also used by many people. So that's why we choose these two subjects. So we first use the PACS with the implemented extension as our test generation tool. So we apply PEX to generate the test input first, and then we apply our approach to collect the information and produce the identify external method call problem and object creation problems. So in our evaluations, we answer 2 research questions. The first research question we answer is like, how effectively can our approach identifying external method call problems and object creation problems? The second question we answer is like, when we identify so many problem candidates, how effectively can our approach like pruning these irrelevant ones? So here is a table showing the the evaluation result. So I give you a highlight is like we identify 43 external method call problems with only 1 false positive and 2 false negative. To identify the false negative, we manually go through all these all these program, and then we identify the problems first manually, and then we compare it with the identified one by our approaches. So next, I will give you some example how our approach is successfully identify the problem and why our approach failed in some cases. So this is the first example. Is actually from the X unit. So first, PEX cannot achieve high coverage of this problem because the external method call here. So after we executed the test, we can see that we collected the coverage, and we see that this branch statement in line 1 is not covered and it has data dependency on the program input. Thus, we report it as external method call problem. Similarly, for this executor, because the method keeps throwing exceptions for all executions, and we check the coverage and we report it correctly. So this is an example like why our approach produce false negative. As we can see, after we check it, we found that okay, this branch is not covered. It actually used the return value of the previous of the external method called open subkit. However, this external method does not have data dependency on program input. It uses a constant input. And after I further check it, I further confirmed that actually is used to read the value from the Windows registration entries. So when I run the test cases, if I want it to cover the other side, I need to modify the registration trees. So that's the one problem missed in our approaches. So in our future work, we may plan to turn every external method call as candidate, and we can check this. But we need more experiment to show that how it will affect the precision and the record of our approach. Next, I will give you an example of how our approach identify the object creation problem on real subjects. So first, PEX also achieve low coverage for these methods. The reason is that to enter this for loop, you need a field type under test to not now, and also it has to implement at least 1 interfaces in the object type because this is the reflection things. And by checking the class structure, by analyze the field declaration hierarchy, we found that okay, this field can be assigned using the public constructor. So we correctly reported the object type of this field. So when we just simply provide a mock object to mock to implement the interface I type in for, these branches can be covered. The other one that we produce false negative is showing here. So actually, this should be similar to the successful cases. However, when we found that the field feature is implemented using the dictionary type, which is not handled correctly by PEX, and we lost the track of the symbolic value there. So yeah, at that time when we were doing the experiments, we did not implement that logic. So we produced some of the false negative. For the false positive of our approaches, there are also one more false positive we get is the static field. So when some branch is related to the static field, we also lost the track of the symbolic value. And yeah, I think like the later version of PEX will fix it, so we can make our And the reason why we have some false positive is like Currently, when we collecting the symbolic expression from PECs, we are usually collect the stream from it. So when we write some code to extract the constraint from the stream, it will have some problem to dealing with some corner cases. That's why sometimes we have false positive. And this is the evaluation tool to showing how we prune the candidates. As we can see in the previous examples, not actually only a few of the external method call will cause problems for automatic text generation tool, and our tool can effectively prune these irrelevant candidates. And also we can see that like to cover certain branches, you actually don't need to provide object type for every field. You only need to provide to some of the fields of the object type. Yeah. So our approach actually is not limited to just assist dynamic symbol execution. Our approach also can assist the other structural text generation approach. For example, because our approach already identified the external method call that will cause problems, so it is possible to use a way to automatically generate mock object for only this external method call. The second thing is like, to assist the random approach, actually is like our approach already identified the object type that will cause problems. So maybe the random approach, they can assign more probability of exploring this pipe. So you have more chances to cover more branches. Besides, some of the advanced method sequence generation approach can also be used. For example, when we identify object creation problem, you can apply some of these expensive approaches to only explore the type that reported by our approaches. Yeah. So the future world of my approach is like, although we don't see many false positive and false negative of our approaches, but we still have some potential issues. For example, currently our approach did not consider the argument side effect of external method calls. So some of the external method calls, when you pass in a program input, it may modify the program input. So it actually will have some problems. And currently our approach only considering data dependencies. So it may happen that some of the cases you need control dependency to help you produce more precise results. But this requires more experiments to try whether combined control dependency, how control dependency will affect the precision record by our approaches. Also, we may plan to leverage static analysis. So because like currently we only analyze the code executed by the text inputs, but some of the regions, if it is not covered by the test cases, we lose the chance to analyze them. So static analysis maybe is also a good way to extend our approaches. The other thing is like, currently the output result of our approaches are some textual output, like tell you that, okay, you have a problem that may prevent you from covering branches 1, 2, 3. It's still very difficult for a developer or tester to understand. So we may provide visualization approaches to visualize the analysis result with the problems. And we also plan to carry out a user study of evaluating the effectiveness. Yeah, so yeah. So here comes the conclusion. Yeah. Okay, so any questions?
So it's interesting that you don't need actually a test suite from PECs to apply this tool.
Yeah.
You can actually take an existing unit test suite and run it.
Yes.
And also collect information.
Yeah. You can actually manually provide the test inputs, and our project can also help you to identify why you cannot cover certain branches.
That's pretty interesting information. Going for the last percentile of coverage that you know they're really dependent on the machine, the environment.
Yeah.
Are you going to integrate this?
I've found 4 more hours per day. But this is great. So it's a well-known issue. We claim we don't have false positive in dynamic symbolic execution, but obviously it's not true object creation and the external methods. It's really a big problem. That's why we build models from the beginning, but there's more work to be done there. Thank you.